Welcome back. So for our first talk of the session, we have Gabriele Vanoni speaking about compiling higher order programs to Bayesian networks.
Okay, thank you very much. So this is joint work with Claudia Faggian, who works with me at IRIF in Paris. So I will start just going back to Popple 2 years ago, where we published a work about Bayesian networks. In that paper, we had this kind of language. We had a first-order term calculus, and then we refined it also to a higher-order one. But in the talk of today, I will stick to the first-order fragment. This is a simple first-order programming language, declarative programming language in a lambda calculus syntax. Of course, there are no lambdas because we are first order. We have probabilistic primitives in the form of a sample from a probabilistic distribution D and of a case construct that we use to encode conditional probability tables, such as the ones that we find in Bayesian networks. And finally, we also have an OBS construct that allows us to observe evidence. Values are the traditional values of the call-by-value lambda calculus, and types, for simplicity, are just Booleans or tuples of Booleans. So what we proved there was that if a lambda term is typable with one of these ground types, then there exists a Bayesian network such that the semantics of the Bayesian network, so the probability distribution defined by the Bayesian network, is exactly the same of the semantics defined by the lambda term. And there exists also the converse statement, but this is almost trivial because it's almost obvious how to encode Bayesian networks inside this fragment. The point is that from every program in this fragment, we can extract Bayesian networks, or at least here we show that it exists. So now the problem could be, how do we effectively extract this Bayesian network from the probabilistic program written in this language? Well, actually, since we proved this result, actually during the proof we also have given a way to extract the Bayesian network, and this is the intuition. Well, this is a probabilistic term, and this is the type derivation of the probabilistic term, but this has been augmented. It has more information with respect to the type derivation with the types that I have already described. In fact, here types are not just Booleans, but they are annotated Booleans. So here we already add to the types the information about the random variables which are actually defined by our program. And so with this type derivation augmented with the information about the names of the random variables, well, then it's possible to retrieve the Bayesian network just by following a sort of information flow graph. So following the occurrences of the types of the names, it is possible to derive a graph, and then we could prove that this graph is actually directed as a cyclic graph, and so actually this graph is the Bayesian network defined by the underlying term. But now the point is, we would like to do this construction without considering the named Booleans. So just by having here a Boolean B and not a Boolean with a name, with the name of the random variables. And this will be particularly important when we will go into the higher order realm, when there are copies of subterms, and so we don't know at compile time how many random variables will be present. So we need something which can act dynamically somehow. And this is why we have resorted, in order to build this Bayesian network out of the term, to an abstract machine. An abstract machine, in particular, in the style of Krivine's abstract machine. So I will show you the basic rules of this machine. They are a bit simplified with respect to the real implementation in order to keep the presentation more easy to follow. Well, when we encounter a let constructor, well, we just record in a data structure called the environment the fact that we have encountered a regex. And so we just record the argument of this variable x, and then we proceed to t. Nothing happens at the level of the probabilistic evaluation, and so this is standard for abstract machines in general. It is standard as well when we encounter a variable. Well, we just jump to the argument which was saved inside the environment. Now, this is the first interesting rule. When we encounter a tuple, actually, our machine is a parallel machine. It has multiple threads, and this is why here it's written with tau union, because actually we are executing a set of threads, and we select at each time just one thread to evaluate. But the machine is morally parallel. And so when we encounter a tuple, what we do is that actually we spawn two different threads, one for the argument which is the left-hand side, and one for the right-hand side of the tuple. So here is when we actually create the parallelism. And this is because in a Bayesian network, if we start from the conclusion, well, maybe a variable depends on a random variable depends on two random variables, and so we have to evaluate the two different branches in parallel. Then, when we encounter a case constant, well, a case constant, this means that this creates a new variable, and so this is why we actually update in our graph data structure that we are always carrying with our state. This is a global graph data structure. We update the set of vertices, adding this new vertex, and this new vertex is named with a new name, and actually we use as name this macro cpos, which is just a macro for saying, well, the name of this node is the tuple term context, so it's the position inside of the term. And then we should add also an edge to the set of edges, and well, this edge is from the last variable that we encountered, that here it's written as p, and we carry it together with our state, and actually this new node that we are adding. And so this is why we are adding the edge p to our current position. And finally, the sample. Well, the sample is exactly the same, so we are encountering a new random variable which has been introduced by the sample construct, but then we don't have to proceed, so the thread just dies, and we add, of course, again the new random variable and the edge, the corresponding edge. So this is our implementation, or better, a simplification of our implementation. And of course, we need to prove also the correctness of this implementation. So what we say is that if we start from the initial state, well, we reach a final state where there are no more threads, and as the graph we obtain that, well, the graph which has the same semantics of the term that we are evaluating. Of course, in order to prove the correctness of this compilation, we need to prove the confluence of the machine, because the machine is parallel, and so we need to be sure that this parallelism is harmless. Well, why are we interested in compiling Bayesian lambda terms to Bayesian networks? I mean, why the target of our compilation is Bayesian networks? Well, maybe because Bayesian networks are very interesting and we are fine with this answer, but there is also another possible answer. Well, actually, it is possible to use quantum technology to fasten the inference on Bayesian networks by a quadratic speedup. And this is well known, at least since 10 years. And in particular, in order to exploit this result, we need to translate Bayesian networks into quantum circuits. And so, of course, if we want to do inference on a program and then to exploit this quantum speedup, well, first we have to translate to Bayesian networks. And so what's the point? The point is that a Bayesian network is a directed acyclic graph, and a quantum circuit is a directed acyclic graph as well. And so the translation is actually quite simple, almost direct, I would say. The topology remains the same. And so, well, we can also exploit these the technology of Bayesian networks to make this compilation more efficient, in the sense that, of course, we need the one quantum bit for each node of the network. Networks have maybe hundreds of variables, and so using technology from Bayesian networks, such as pruning, so we can reduce the number of bits needed by just considering the part of the network that we are interested in. Or using conditional independence, well, we can split the network into different networks, and so reducing the maximum number of used qubits. And so this is it. Just for future work, well, we are going to use also higher order programming languages and to cover PCF or call by push value, and to implement then the full stack from a probabilistic programming language to quantum circuits and evaluate it on benchmarks. Thank you.
Thanks very much. So we have time for a question or so while the next person sets up. If they could come forward, please. Questions? Yeah, you go.
What's stopping you going higher order now? Because the abstract machine is already, you have everything you need to.
No, well, yeah, we have started with the first order case, and then, I mean, the abstract machine has not everything we need. I mean, to go higher order is, I mean, we think we know how to do that, but at the same time, it's not exactly trivial. Yeah, because the point is the copy mechanism of higher order computation. So, I mean, at runtime, you will have random variables which are not identified anymore by the position inside the term, but we have to copy, let's say, linear logic boxes. And so, I mean, you need to devise a more complicated way to do that. And also, if the evaluation order becomes really tricky, in the sense that when you are first order, every evaluation order is the same, roughly, because you're linear. But then it's more difficult to deal with a call by value or call by name or call by push value. So, yeah.
Thanks.
Well, thanks. Let's thank the speaker again.